I am Kamran and I will be talking to you guys about how we can recognize small gestures such as keystrokes using Wi-Fi signals. So this is a joint work with my supervisor Alex Liu and my colleagues Wei and Shehzad. So why is it important at all to study keystroke recognition systems? First of all, new wireless keystroke recognition systems can be used to realize new technologies such as virtual keyboards where people can type on printed keyboards. While on the other hand, such schemes can also be used can also pose a security and privacy concern to the users where attackers can eavesdrop on what users are typing. Several keystroke recognition schemes have been proposed in the past. For example, uh, video-based schemes where people analyze videos of users typing on a keyboard, or analyzing sounds or electromagnetic radiations which are emitted by the keystrokes while typing, or even recently using STN as software-defined radio-based custom receiver designed to recognize keystrokes. We, on the other hand, ask the question, can we recognize keystrokes using commodity Wi-Fi devices? And the answer is yes. We propose YKey, which is a keystroke recognition scheme which uses channel state information extracted from commodity Wi-Fi devices to recognize keystrokes. So YKey is based on two key observations. The first key observation is that obviously that keystrokes impact Wi-Fi signals because they introduce multi-path changes at the receiver side. And the second observation is that different keystrokes impact Wi-Fi signals differently because hands and fingers of a user move in certain direction and formation for different keystrokes. For example, here you can see the process CSI waveforms of two keystrokes which are adjacently placed on the keyboard, but they are fairly different from each other. However, like recognizing keystrokes using commodity Wi-Fi devices is a challenge because keystrokes are relatively small gestures as compared to like hand waving or pushing, pulling, etc. And they constitute small amount of motions. They are closely placed on the keyboard and they are closely spaced in time as well. So the key challenge here is to detect and extract the keystroke waveforms from the CSI data collected from the commodity devices. The first step in YKey is noise reduction. So as you know that the CSI values reported by commodity Wi-Fi devices are noisy, and they contain bursty noise, and both due to the hardware limitations and multipath interference. So we first of all use low pass filtering to reduce that noise. We also observed that the CSI variations in different Wi-Fi subcarriers are correlated. What that means is that among the 30 groups of subcarriers per antenna stream, like the 30 groups of subcarriers per antenna stream, the CSI data collected from them actually contains redundant information for different keystrokes. So what we do is we apply a trick. We utilize this correlation redundancy, and we apply principal component analysis on the subcarriers in order to extract the top few components which represent the keystroke variations only, and get rid of the noisy components. So basically we can get rid of the noisy unrelated variations and only keep the components which represents the keystrokes only. For example, here I show 4 PCA projections from CSI data collected for one of the keystroke. So as you can see that the top PCA component here is the most noisy one, and if we remove this component, we get clean CSI waveforms which we can further use for processing, for example to extract and then recognize keystrokes. So essentially this PCA based noise reduction scheme helps us get rid of these unrelated noisy components and only keep the components which represent keystrokes. The next step after noise reduction is the keystroke extraction. So how we can extract the CSI waveforms of the keystrokes from multiple keystrokes in the CSI data. So for keystroke extraction, we utilize the observation that the CSI waveforms of different keystrokes, they show typical increasing and decreasing trends in the rate of change of CSI values. So our keystroke extraction algorithm, it processes all the CSI waveforms from all the antenna streams, and then it robustly estimates the start and end points of the keystroke waveforms by combining the results from all the antenna streams. And these start and end points can then be used to extract the keystroke waveforms from the CSI data. The next step is feature extraction. Once we have the keystroke waveforms, we have to extract the features from those waveforms. In order to utilize the maximum detail in the CSI waveforms, we choose to use the shapes of the CSI waveforms to be used as the features, and we use discrete wavelet transform in order to get the compressed shape features from the keystroke waveforms. And we actually apply the DWT 3 times consecutively in order to reduce the computational complexity of our classification process. So here I show some examples of the feature extraction process. So these are some of the extracted CSI waveforms of the keystrokes, and here are of the key I, and here are some of the DWT features of keystroke I. Similarly, on the right hand side you can see the DWT features of keystroke O. Like you can see that even after almost 8 times the compression, the keystroke waves are the keystroke shapes are preserved, and they are fairly different from each other for different keys. The next step after keystroke extraction is classifier training. We use dynamic time warping as a comparison metric between different keystroke features, and we use KNN classifiers in order to classify for our classification process. So we train an ensemble of KNN classifiers, so where each classifier is trained using one of the keystroke waveforms from all the one of the extracted keystroke waveforms from all the antenna pairs. And in the keystroke recognition process, the results from all the classifiers in the ensemble are combined using majority voting in order to obtain a final decision. So now that we have discussed the different parts of WiKey, let's move on to the data collection part. So in order to collect data, we use the famous Intel 5300 NIC for CSI collection, which was installed on a laptop, and a TP-Link router. The laptop was set to send an ICMP ping request to the router in order to sample the CSI values. We collected data from 10 users for both separate keystrokes and the sentences, and we asked the users to keep the inter-keystroke interval to be approximately 1 second and type one key at a time. So moving on to the evaluation. So first of all, we will show how well our keystroke extraction performs. So we show that our keystroke extraction algorithm performs very well, and it achieves accuracies of more than 95-97%, averaged over all of the users we collected the data from. However, we did notice that our algorithm missed some keystrokes, which happens either due to the fact that some users have inconsistencies in their typing behavior, or in the cases when the keys which are being pressed, they constitute small amount of motions, for example J or F, which like usually are directly underneath the fingers of the user when he is typing. So so this is the keystroke extraction accuracy performance results. Now let us move on to the classification accuracy. So first of all, we tested the accuracy of our classifier on the single keystrokes. In the first experiment on single keystroke, we tested 37 keys, the alphabets, digits, and the spacebar, and we used 30 samples per key for our cross validation process. And we show that the 10-fold cross validation accuracies of 83% were achieved, averaged over all the users and the keys for when we tested all the 37 keys. On the graph, you can see that the x-axis shows the user IDs and the y-axis shows the accuracies which were achieved. So we tested in this experiment, we tested both cases, and in first case we tested all the 37 keys, and in the other case, in the red bars show the accuracies results for when we tested only the alphabets. So we observed that in slightly smaller accuracies in the case when all the 37 keys were used. So the major reason behind it is the similarity in motion, similarity in the motion when we are pressing keys on the QWE row of the keyboard with the digit row of the keyboard. In the second experiment was performed only for user 10. So we studied the impact of increasing the percentage of training in that set from 50 to 90% by increasing the folds in the cross-validation process of Y key. The keys tested here were only alphabetic keys, and we increased the samples from 30 to 80 this time. We observed that the multi-fold cross-validation accuracies stayed above 80% for different folds, although the accuracies for the keys like J, K, V, they dropped below 60% in the case when only 50% of the data was used for training this. So this again happens due to the fact that these keys, like, they constitute smaller amount of motions as compared to the other keystrokes typed by the users. So that's the main reason behind this drop in the accuracy of these keys. Okay, moving on to the classification accuracies for the sentences. So we tested the accuracies of our classifiers on, like, first of all, on one sentence typed by all the users 2 times. So, and we used 30 training samples per key in this experiment, and we observed an overall average accuracy of more than 77% for different users. We observed that for some users the classification accuracy was pretty high, like around 90%, and for some it was 55. Like, this again happens because people, like, when users are typing sentences, they have slightly different typing behavior as compared to the case when users are typing single keystrokes. So yeah, let's now moving on to the second experiment on sentences. So this experiment was again performed only for user 10, and we increased the number of training samples from 30 to 80 this time, and we tested our results on 5 sentences which were repeated 5 times by the user. And we saw that the average accuracies, they increased from 80 to more than 90% in this case, and the highest accuracy achieved was 100%, and the worst case was around 80%. Okay, now that we have discussed the different parts of Y key and its performance, let's discuss some of its limitations. So right now the Y key has only been tested in the interference-free surroundings. So like, it requires that there is no other major motion occurring in the environment while the user is typing. And second, that the Y key will be affected by changes in the setting, like if you move the places of Wi-Fi devices, you will have to train the system again. And right now Y key only supports relatively slower typing speeds of around 15 words per minute, and it requires relatively quite high CSI sampling rate in order to get high resolution CSI waveforms in order to achieve higher accuracies. And again, similarly, it requires many training samples per key in order to achieve reasonably well high accuracies. So let's conclude the talk. I presented in this presentation the Y key scheme, which is a Wi-Fi based keystroke recognition scheme which uses commodity Wi-Fi devices, and we showed that correlations in the Wi-Fi subcarriers can be used to remove the noise in CSI data. We proposed a robust algorithm for keystroke extraction, which can also be applied to other fields of human computer interaction which use commodity Wi-Fi devices. We show that the shapes of CSI waveforms, they prove to be very effective features for recognizing small gestures such as keystrokes. And finally, we show that Y key can achieve more than 90% keystroke recognition accuracy in controlled settings for reasonable typing speeds. So thank you. If you have any questions here.